Hi guys, today we're going to be covering section 12.5 known as Volume-Volume Stoichiometry, and let's get started. So today's topic is starting off by talking about propane, that is how much propane that's left in a tank, right? And those of us who own gas grills, we know that this is a question that we always ask ourselves. And I know that because we have a gas grill, and when it gets really light, we're like, oh, should we cook out or should we not? Because what if we don't have enough propane? And then if we don't, my husband usually has to stop in the middle of the process, go get a new tank, and it's just plain annoying. All right, so how much propane is left in the tank? Who's going to volunteer?
As the weather gets warmer, more and more people want to cook out on the back deck or backyard. Many folks still use charcoal for grilling because of the added flavor, but increasing numbers of backyard cooks like to use a propane grill. The gas burns clean, the grill is ready to go as soon as the flame is lit. But how do you know how much propane is left in the tank? You can buy gauges at the hardware stores that measure gas pressure and tell you how much is left in the tank.
Very good. Thank you, Miss Alexia. So yes, we can figure out the volume of whatever's left in the tank by measuring the pressure, right? If you know your gas law, which of course I do, you can compare the original pressure to the new pressure and the original volume and calculate what you have left over. Okay, and that's just basic gas law. That's actually Boyle's law. Okay, is it Boyle's law? Charles' law. No, Boyle's law. But that's a discussion that we're going to have in very, very soon, probably next week or the week after that. But either way, you can figure it out as long as you have a pressure gauge, right? A pressure gauge is something that you can go and get at it at the hardware store like Lowe's or Home Depot. You can even get a pressure gauge like for tires and stuff at AutoZone. I blanked out for a second. But yes, you can use that pressure and you can figure out the volume of whatever you have left over. And that way you don't have to worry if you have enough. But today, let's get to today's topic. Today's topic is volume-to-volume stoichiometry. And we're starting off by talking about Amadeo Avogadro again, right? He's the one who gave us Avogadro's number, right? Well, he also did some hypothesizing. He also did some thinking about volumes of gases. And he came up with a hypothesis, right? He said, well, I think his hypothesis states that equal volumes of all gases that are at the same temperature, and pressure will contain the same number of gas particles. Further, we can explain this. So basically what we're trying to say is that if you have 1 mole, if you have 1 mole of any gas, and remember, gases, we're talking about oxygen gas, hydrogen gas, helium gas, nitrogen gas, carbon dioxide, nitrogen dioxide, all of those, carbon monoxide, all of those gases, if you have just 1 mole of it at STP, which is standard temperature and pressure. Standard temperature, if you didn't know, is 0 degrees Celsius. Standard pressure is 1 atmosphere. So if you have 1 mole of oxygen, 1 mole of carbon dioxide, 1 mole of hydrogen gas, they're all going to have the same volume, 22.4, 22.4, 22.4. It doesn't matter if I'm talking about chlorine gas. If I got 1 mole at STP, 22.4. If I have 1 mole of fluorine gas at STP, 22.4 will be its volume. The volume does not change if you have 1 mole of it at STP. Any gas. This applies to any gas. So these characteristics make stoichiometry problems involving gases at STP. Very straightforward and very, very easy. Okay. Consider the reaction of nitrogen and oxygen gases when they form nitrogen dioxide. And we see the formula or the equation below. So let's check it out, let's analyze it, and let's talk about it. So what are the coefficients? What are the numbers in front of each compound? Remember, if there's no number in front of the compound, that means there's just one. So nitrogen, 1. Oxygen, 2. Nitrogen dioxide, 2. And we could change it and we could talk about it in terms of molecules, right? Because they're all molecules. They all have a covalent bond that's holding them together. So we can say nitrogen gas, 1 molecule. Oxygen gas, 2 molecules. Nitrogen dioxide, 2 molecules. And we could talk about it in terms of moles, right? Which is the stoichiometry that we've been working with. Everything that we've been working with before was all about moles, right? When we looked at the reaction, we were looking at those in terms of, okay, I'm changing moles of compound A to moles of compound B, right? So we can say that 1 mole of nitrogen plus 2 moles of oxygen will give us 2 moles of nitrogen dioxide. Okay, that's what we did Monday and Tuesday. Today, we're going to talk about it and think about it in terms of volume. And you have to remember, what's the unit for volume? L for liters. L for liters. So what can we say about these gases in terms of volume? Well, we can say 1 liter or 1 volume of nitrogen plus 2 liters or 2 volumes of oxygen will produce 2 liters or 2 volumes of nitrogen dioxide. Okay, so we're sticking to the bottom numbers for today. Everything's going to be in terms of volume or liters. Okay, but before we do that, you have your first pair deck question. What is the number of liters that is equal to 1 mole of any gas at STP, standard temperature and pressure? What is the number of liters that is equal to 1 mole of any gas at STP? And I just repeated that number like 5 or 6 times. What's the volume? How many liters will 1 mole of carbon dioxide, 1 mole of oxygen, 1 mole of fluorine occupy? What's the volume, guys? Anybody remember? If you're in Pear Deck, you can answer on Pear Deck. If you just got here, because I know some of you just did, there's the link to Pear Deck. Okay, so Efrain got here, Jose and Jeremiah. Efrain, Jose, and Jeremiah. Hold on, where's Jeremiah? Here's Jeremiah. What did we say? What was the volume? Anybody remember? I repeated it like 5 times earlier. Anybody remember? How many liters does 1 mole of any gas at STP occupy? You don't remember, Ms. Diamond? Oscar? Irvin, you don't remember what I said? How many liters does 1 mole of oxygen occupy when it's at STP? I'm waiting, I'm staring at the chat, I'm checking on Pear Deck, no responses. No responses. Oh dear, dear, dear. Oof. Oh, very right. I got somebody typing. Let's see what they're writing. Nope, they haven't written anything. Okay, do I have to go back to the last slide? Well, let's give them a second. Maybe they're just typing it or writing it out and they need a second. Let's give them a couple seconds. Nope, Don't see anything. All right, let's go back. 1 mole of any gas at STP occupies what volume? Anybody see it? 1 mole of any gas, how much does it occupy at STP? Hello? If you have 1 mole of any gas at standard temperature and pressure, how much volume will it take up? Come on, guys. I'm waiting. I'm staring at the chat and I don't see anything. Did everybody see it? Oscar. Read the second sentence for me, Oscar. Oscar Mendoza, are you there? Jeremiah, read the second sentence for me.
Occupies about 22.4 liters.
That's it. Any gas at STP, standard temperature and pressure, will have the same volume, 22.4, 22.4, 22.4. Remember that, Jeremiah, because it's going to come up later. Okay. Because of Avogadro's work, we know that mole ratios between substances in gas phase reactions are also volume ratios. Okay? And we already discussed that, right? The 6 possible volume ratios, which is the same thing as mole ratios, are shown for the above equation. Okay? So all they're doing is they're using the coefficients, right? The numbers in front of the compounds to make a ratio between elements, between these compounds. In the first example, they use 1 volume of nitrogen gas, and they compare it to the second compound. 2 volumes of oxygen, and you can see it here. 1/2, nitrogen over oxygen. And then they said, well, you can also flip it. You can put oxygen on top, nitrogen on bottom, and you'll have the same ratio, right? Except instead of it being 1/2, it's now 2/1. But it's the same compounds involved. All they did was they flipped. In the second one, they compare your first compound, nitrogen, to your third compound, nitrogen dioxide, and they use the volume. 1 volume of nitrogen is equal to 2 volumes of nitrogen dioxide. Or you can put nitrogen dioxide over nitrogen and have the same ratio, just flipped. 1/2 becomes 2/1. In the third volume ratio, they take your second compound, oxygen, and they compare it to nitrogen dioxide, NO2. 2 volumes of oxygen is equal to 2 volumes of nitrogen dioxide. And again, all they did is they flipped it for the second one. They put nitrogen dioxide over oxygen. And again, 2/2. 2/2, they've just flipped the compounds. Everybody got that? The volume ratios above can easily be used when the volume of one gas in a reaction is known and you need to determine the volume of another gas that will either react with or be produced from the first gas. Excuse me. The pressure and temperature conditions of both gases need to be the same. So the only thing that you have to remember is that the reaction has to happen in the same temperature and the same pressure in order to use these conversions or these ratios. So remember, anytime you're doing stoichiometry, it's all about practice, practice, practice. The combustion of propane produces carbon dioxide and water vapor. What volume of oxygen is required to completely combust 0.650 liters of propane? Okay, that's question number one. There's actually two questions in this one. The second question asks, what volume of carbon dioxide, excuse me, what volume of carbon dioxide is produced in the reaction? Let's go to Jamboard and figure that out. Anytime they give you a problem, always identify what they're giving you and what they're asking you for. And every single chemistry question will give you some information and ask you for something else. So this is my given information. This right here is what they're asking me for. Propane, oxygen. This would be considered like my A compound. This is my B compound. So I want you to think of the liters of propane as the same as being moles of compound A. And when they're asking you for volume of oxygen, I want you to think about it as moles of compound B, all right? Anytime we're switching from A to B, we need to use the reaction to do that switch. We need to do that ratio, right? So always start with your given information. And my given information for the first one is 0.65 liters, of propane. And remember, anytime you're doing dimensional analysis, your given has to go over one. You got to draw times, a line, and then the arrow. Remember, the arrow helps you remind you where you need to put things or the units in order to cancel. This is all about the units. Whatever units are crossed out at the top of the arrow need to follow the arrow down. Okay, so if I got liters of propane need to go on and follow the arrow. Okay, so if my propane's on bottom, my liters of oxygen are on top. So my question to you guys is, where do my coefficients go? And you got to remember the coefficient for propane, is 1, right? So 5 over 1 or 1 over 5? What shall I write? 5 over 1. And you can see here the 5 liters of oxygen. So anytime we have numbers on top, we multiply, right? Everybody remember that, right? So what's 0.650 times 5? That's a calculation that you guys have to do for me. I'm not going to do it. This is an easy calculation. Come on, guys. Help me out. What's 5 times 0.650? Very good. 3.25 liters of oxygen. Okay? That's just the first question. And I actually okay. That's the first question. There's a second question. And let's circle what they're asking me for, the second one. They're asking me for volume of carbon dioxide. Here's carbon dioxide. So now my B is right here. We are converting propane to carbon dioxide. We're starting with the same given information. We're still starting with 0.65 liters of propane. So I'm going to put in here 0.650 liters of C3H8. I'm going to put it over 1, and I'm going to start my dimensional analysis process, right? That's how we start all dimensional analysis. Okay? Where do liters of propane need to go? They need to follow the arrow, and the arrow points down, right? So I'm going to put in here liters of C3H8. Okay? So that means liters of carbon dioxide go on top. 1/3 or 3/1? What shall I do? 3/1 is correct. Everybody see why the 3 is on top? Look at where carbon dioxide is. So what's 0.650 times 3? Very good. 1.95. Sorry, I ran out of room. I always write too big. All right, what do you think? It's not that bad, right? It's not that bad. At least it's a lot easier than what we were doing yesterday, right, guys? It's definitely a lot easier than what we did yesterday. Okay, let's go to the presentation and let's figure out and verify our numbers are correct. Exactly what they came up with. 3.25 liters of oxygen and 1.95 liters of carbon dioxide. Step 3 says to think about your result. Because the coefficients of oxygen and carbon dioxide are larger than that of propane, the volumes for those two gases are greater. Note that the total volume is not necessarily conserved in a reaction because moles are not necessarily conserved. In this reaction, 6 total volumes of reactants become 7 total volumes of product. Alrighty, so your second Pear Deck question. Now I want you guys to try this out. How many liters of potassium iodide were used if 8.5 liters of iodine are produced at STP? Who wants to try it? Anybody want to try it? All right. Anybody? Miss Diamond, you don't want to try it? I think you can handle this. I think Jeremiah can handle it, or Oscar. But are they brave enough? Come on, guys. You should be able to try to do this. At least this one. This one is easy. It's a one-step process. Any volunteers to try this? I don't mind doing it, but you're going to tell me what to do. I don't mind doing it, but you need to tell me what to do. How many liters of potassium iodide were used if 8.5 liters of iodine gas are produced? So remember, circle your given information and what they're asking you for. Okay, this is iodine gas right here. This is potassium iodide. This is my B. This is my A. What do I do? I know I need to start with the given, but what does the given go over? I know I need to start with 8.5 liters of iodine, but what does it go over? It goes over 1. Very good, Ms. Diamond. And then we set up our dimensional analysis. We put times, a line, and then the arrow. What do I do next? Where do my units of iodine need to go? Where do liters of iodine need to go? Where do liters of iodine need to go? Okay, very good. So liters of I2. Okay. Where does potassium iodide go? Liters of potassium iodide. So liters of Ki. Okay. What are the numbers? I need numbers. What do I need to put? 1 over 1, 2 over 2, 1 over 2, 2 over 1. There's a lot of numbers out there. Which ones do I use? Two over 1. Very good. So if I do 2 over 1, what's my final answer? I haven't heard from you today, guys. Ms. Diamond is doing all the work, and it's pretty annoying when I have a lot of other students here that are capable of helping her out. Oscar, Alexia, Irvin. If I have 8.5 and 2 and I multiply, what do I get? Very good. 17 liters of potassium iodide. All right, and that is correct. That is the correct answer. Very good. All right, let's watch the video. I have it ready. You calculate. And I want you to look at what he does today. I want you to look at what he does today because he's going to do 3 steps. Out of the 3 steps, 2 of them are not needed. 2 of them are not needed. I want to know if you're able to recognize where he's just repeating himself. He's repeating himself in a way that he doesn't have to. Okay? Check it out. Stoichiometry problems, volume. We first have to understand that standard temperature and pressure at STP 1 mole is equal to 22.4 liters. 1 mole of any type of gas will occupy 22.4 liters. Knowing this, look at this equation here. We have 2 moles of carbon dioxide plus 1 mole of oxygen yields 2 moles of carbon dioxide. How many layers of carbon dioxide produces 75 layers of carbon dioxide of carbon and oxygen? So we have 75 liters of carbon monoxide. How many liters of carbon dioxide are produced? Well, the first thing we have to do from here is we have to figure out how many moles 75 liters of carbon monoxide are. In doing so, we must use the mole to volume equation. We know there are 20 there are 22.4 liters of carbon monoxide in 1 mole of carbon monoxide. These will cancel out.
leaving us with 3.35 moles of carbon monoxide. From there, we take that answer and we use moles of carbon monoxide and convert 3.35 moles of carbon monoxide. We know for every 2 moles of carbon monoxide, we can produce, this should be carbon dioxide. We can produce 2 moles of carbon dioxide. Okay, here, moles of carbon dioxide cancel out. Actually, if you're very good at math, you'll see that the 2's will cancel out and the number will stay the same. And it's because we exchange units to now 3.35 moles of CO2. But that still left us how many liters of carbon dioxide. So then we must take 3.35 moles of carbon dioxide, which we'll move down here, 3.35 moles CO2. And we know there are 22.4 liters of CO2 in 1 mole of CO2. Moles cancel out. And what we'll realize we'll come up with the answer would be 3.35 times 75 liters of CO2.
Anybody see it? Does anybody see which calculations are not needed? There's 2 of them that are not needed because he's doing the same thing. He's using the same numbers. Where? Where is he using the same numbers, guys? In the first calculation, the second calculation, or the third calculation? There's 2 of them that are exactly the same, that he's using the same numbers. Where is he using the same numbers? And just look at the numbers. You don't necessarily have to look at the units. Where is he using the same numbers? In the second one. Okay. But I can understand why he's using the same numbers because the coefficients are the same. Where else are they the same, Diamond? And I'm saying the same numbers in separate calculations. Look at 22.4. Does 22.4 come out more than once? Check this out right here. Do you see how 22.4 liters and 1 mole is coming out in the first calculation? And then he uses the same numbers on the last calculation. We've talked about the fact that if you got numbers on top and bottom, it doesn't matter if they're in the same calculation, they'll still cancel each other out. Look at the 1 mole. Isn't the 1 mole on top and then the 1 mole on bottom? They cancel out as well. So did he really have to do the first calculation and the last calculation? Not really. The only thing that he had to do was the middle calculation, where he's using the volume or the mole ratio to change from compound A to compound B. We're smart enough to recognize the use of those numbers, so we don't do that extra work that he did. All right. In summary, calculations of volume to volume ratios are based on Avogadro's hypothesis. Pressures and temperatures of gases involved need to be the same. So anytime you're dealing with gases, as long as they're at the same temperature and pressure, you should be able to do this method. Review questions. What is Avogadro's hypothesis? How much volume is occupied by 1 mole of a gas at STP? In the sample problem above, assume we combust 1.3 liters of propane. How much carbon dioxide will be produced?